Our second speaker of the day is Anna Schenfisch, who will be speaking to us about a faithful discretization of the persistent homology transform.
All right, thank you. I'd like to start by acknowledging my collaborators, Brittany Fazy, Samuel Micka, David Millman, and Lucia Williams. So in this talk, first we'll give some background definitions and information leading up to a definition of what the persistent homology transform is, and give some indication why we might want to discretize it, what discretization means, and what it means to have a faithful discretization. And then we'll discuss how reconstruction can be used as a proof method to show that a discretization is faithful. Then we'll get into the reconstruction itself, going in order of increasing dimension. And then finally, we'll end with some discussion about how these methods can be extended to other topological descriptors. So let's first define what a lower star filtration is. So given a particular direction S, here it's indicated by this upward arrow, we can filter up through space, recording the sublevel sets. So what happens at or below a particular height in this filtration. So for example, at this first height, we would see that there is one connected component. We would continue to see just one connected component until this height, when we would see the introduction of another. And we would proceed in this way. Eventually, we see the cycles born. And at the top of the complex, we reach a point past which no interesting homology changes occur. I'd like to go ahead and give a name to these horizontal lines that I used in my illustration. I'm going to call them filtration lines, or perhaps filtration hyperplanes in higher dimensions. That'll just be useful in our discussion and for visualization purposes. So that's just that all heights in the Euclidean space that occur at the same height with respect to the direction of filtration. So using a lower star filtration, we can then create a persistence diagram. So fortunately, it was discussed in the last talk what a persistence diagram is. So I'll kind of breeze through that. We have a record of homological features as we proceed through the filtration. So on the x-axis, we see the birth heights, so when things first appear. On the y-axis, we see the death heights, so when things merge with an elder feature. Now you may notice that in my version of persistence diagram, I have on-diagonal points that are distinguished. So if you'd like, you can consider this or call it an augmented persistence diagram. Although it's important to note that in reality, most common persistence algorithms actually do compute these on-diagonal points. If you think about sort of the standard method of taking a matrix and reducing it down to compute persistence, there's often a column and a row for every simplex. So with that, you can kind of think about that over on the left as meaning that at this height, for example, we would first see a vertex, and then immediately afterwards, we would see this edge. So there's an instantaneous birth and death of a connected component, and that gives us the on-diagonal points. The main takeaway from all of that discussion is just that in the persistence diagrams that I'll be using today, there's an event at every vertex. And I may refer to these as just persistence diagrams or just diagrams, but I do always mean these augmented versions with on-diagonal points. So now we're ready to define the persistent homology transform, which is abbreviated PHT. So given a particular simplicial complex embedded in Euclidean space, the PHT is the set of all directional persistence diagrams generated by the entire sphere of directions. So I have a little video of that I think is helpful. So suppose that this is our underlying simplicial complex. Here we can see the filtration lines changing as the direction of filtration changes. And then over on the right, we see a video of the changing persistence diagrams associated to each direction. So this uncountably infinite collection of diagrams forming this movie is what the PHT is. So the PHT is actually what we call faithful. And by that, I mean that no other simplicial complex could have generated the same set of diagrams. So the movie that we just saw uniquely corresponds to the simplicial complex that generated it. So in particular, one important thing to notice is that if we can ambiguously reconstruct the underlying simplicial complex, using a particular set of diagrams, that means that that set of diagrams is faithful. So if I hand you a stack of persistence diagrams and you can tell me what generated all of them, then that collection of diagrams is a faithful set. So why might we want to discretize the PHT? Why might we want to go from this uncountably infinite sort of movie to a finite set of diagrams? Well, besides just a mathematical interest, there have been some uses in applications. So for example, suppose you're comparing similarity between two shapes. Perhaps you have meshes on surfaces or something similar. It's reasonable to think that it might be a good idea to instead compare sets of diagrams. So if you have sets of diagrams that represent each shape, then you can use one of the various metrics on diagrams, which of course have potentially nice stability results. Another potential application is that suppose you want to store some shape, again like a mesh or some other complex perhaps, that's very expensive to store. You might hope that it's possible to find a finite set of diagrams that uniquely corresponds to the shape, but that uses less storage. So the PHT was first defined in 2014 by Turner et al. And in that paper, they showed that the PHT is faithful. So the uncountable set of diagrams is faithful. Then later, Curry et al. Bounded the size of a faithful discretization of the PHT. That was assuming some bounded curvature on the underlying simplicial complex. And then in 2018, Belton et al., that's us here at MSU, we found a faithful discretization for graphs embedded in arbitrary dimension. And that proof involved a reconstruction method as the proof tool. So our current contribution then is expanding on the results of this third bullet point and giving a reconstruction method for arbitrary simplicial complexes in arbitrary finite dimension. So again, just to really drive home the point here, we know that if we have an infinite set of diagrams, we can unambiguously reconstruct the underlying simplicial complex. Our goal is to do so with a finite set of diagrams. And so we'll proceed by building up our set constructively using an oracle. So we feed our oracle a direction from the SD-1 sphere, and the oracle will return the persistence diagram generated by a large-scale filtration in that direction. So it's our oracle knows what the underlying simplicial complex is, but we do not. So let's get into the reconstruction method. So we'll start with vertices. A vertex in RD, of course, can be described by D coordinates. However, the vertex reconstruction method can't be as simple as just choosing D linearly independent directions. The issue here is that we don't know how to pair the heights. So what do I mean by that? Suppose we're looking for the vertices and we first ask the oracle for the information in this upward direction. So from these horizontal filtration lines, we know that there is a vertex at every height indicated here, but we don't yet know where on the horizontal lines they lie. So if we come in with a second direction, we know that there are vertices on every vertical line. However, there are n squared possible vertex locations, right? We know a vertex happens at the intersection of these lines, but we don't know which intersections. So the trick here will be to come in with a tilted direction that geometrically guarantees we won't have any more than n three-way intersection points. So there are various ways to do that. One way is to choose the shortest and widest box in this grid and choose an angle so that we avoid the diagonals. But regardless of how we find that tilted direction, here's an example of what that would look like. We then have exactly n intersection points corresponding to the locations of the n vertices. This is a little bit hard to see in this picture, so let's overlay the underlying simplicial complex. So everywhere you see a vertex, indeed, we see three-way intersections. And then in higher dimensions, of course, we can use similar methods. So one good way to do it is take the E1 direction and tilt it towards the remaining basis directions. A little foreshadowing here, this tool of finding a tilted direction is going to come in handy later. And there are lots of nice properties about tilting it, namely that we have some control over the order of vertices. Okay, so let's move on to how we reconstruct the edges. So our main tool for edge reconstruction is called the in-degree of a vertex. So the in-degree of a vertex in a particular direction is the number of edges adjacent to V and below V. So in this particular example, the in-degree of V in this indicated direction is 4. And we can compute in-degree by adding up the 0-dimensional depths and 1-dimensional births that occur at the height of V. So in this example, we have 2 off-diagonal depths corresponding to these connected components merging with the elder one. And then we have 1 on-diagonal depth, that's the instantaneous birth and death at V. And then of course we have 1 cycle that's born at the height of V. So that gives us our correct count of in-degree of 4. So then using this tool, we're going to proceed using a sweep line algorithm. So we'll sweep up through the vertices, and at every vertex, we'll find the edges above the vertex that are incident to that vertex. And to do so, we'll do like a binary search. So let's run through an example of that. And here it looks like we're in R2, but you can imagine if we're in higher dimensions, with some general position assumptions, we could project down to a plane. So in our sweep line algorithm, suppose that we have processed all vertices below this V. So we know all edges that begin below V. And we're trying to find edges incident to V and above V in this pink region. And as a helpful tool, the true graph is indicated by these gray lines, but pretend that that's unknown. So really, there could be edges to any one of these vertices. So the first thing we'll do is we'll use our tool of in-degree, and we'll measure the in-degree of V in this indicated direction. We would see that there are 2. So we know that there are 2 edges adjacent to V in the pink region. Now our binary search begins. We split the vertices radially sorted in half, and we compute the in-degree in this indicated direction. Here we would see that the in-degree of V in this left side is 2. We know that one of the edges contributing to that total is VV5. So that tells us that there must be 1 edge either to V1 or to V2. So we'll split our vertex set in half again, compute the in-degree again. We see that the in-degree of V in this direction is again 2. And that tells us that there must be the edge VV1. Furthermore, it tells us that there is no edge VV2. Then we would continue processing the right-hand side in an identical way. And then once we found all the edges adjacent to V in this pink region, we would then continue our sweep line up, and we would move on to the next highest vertex and repeat the process for V1. So now that we have this method for reconstructing edges, we can move on to reconstructing higher dimensional simplices. So we have a similar tool called the K-in-degree. So given a particular face sigma, simplex sigma, and a direction S that's perpendicular to sigma, the K-in-degree of sigma is the number of K simplices under sigma that contain sigma as a face. So in this image, sigma is this dark gray 2 simplex, and so the 3-in-degree of sigma would be 1, right? There's 1 tetrahedron below sigma that contains sigma as a face. So we might hope that we could do a similar calculation as we did in edges, where we can just add up the K-1 births with the K deaths. But unfortunately, as we see in this example, that will often be an incorrect calculation. So in this example, this equation would actually give us a result of 3. It's unable to distinguish this middle tetrahedron, which is really what we want to count, from the tetrahedron that are kind of hanging off. So here's where the tilted direction from before is going to come back for the first time. The way that we correct this overcount is using tilted directions on every face of sigma. So starting with vertices, so we find a tilted direction so that the most important thing, I guess, is that V0 is below V1 and V2. We compute the 3-in-degree of V0 in this tilted direction. Here it happens to be 0. There's the 3-in-degree is 0. V1, the 3-in-degree is also 0. But then at V2 in this tilted direction, we detect this tetrahedron that's hanging off of V2. So we subtract it from our overcount. Then we move on to edges. We would see a 3-in-degree of 0, of 0, and then of 1. So we subtract that from our overcount. Now we've processed all of the faces of sigma, so our total is the correct in degree of sigma in direction S. So then using this tool of k in degree, we can describe a predicate for determining if a set of vertices forms a k-simplex. So here's another example of using the tilt procedure. So I think a picture is helpful here. So we'll use two tilted directions to form a wedge around the possible k-simplex. And I mean a wedge of the filtration hyperplanes. So in this example, suppose we're trying to test if a 2-simplex exists between the edge V1, V2 and V8. So our wedge is chosen specifically so that the only vertex in this wedge region is V8. So then by computing the in degree in these two directions of the edge, we will be able to detect if a 2-simplex exists. Namely, the difference of the in degree in this first direction and the in degree of the second direction will be the key. So if the difference of the in degrees is 1, that indicates that as we swing from this lower direction to this higher direction, we added a 2-simplex somehow. But again, the only difference between things below this direction and things below this direction is the presence of vertex V8. And then, so if the in degree difference is 0, we know that there is no 2-simplex present. So we discussed a method of reconstructing vertices, of reconstructing edges, and all higher dimensional simplices. So we've taken in totality, we've described an algorithm for reconstructing an entire simplicial complex. And the most important takeaway from that is that that implies that the collection of persistence diagrams we used, which was a finite set, forms a faithful discretization of the PHT, an explicit one at that. So in the method that I just finished describing, really all we needed to know was the heights and dimensions of events. There's more information in a persistence diagram, right? We know the pairing of births and deaths. We never really used that. So the cool thing about that is that other transforms that also return heights and dimensions of events, for example, the Betty curve transform, are also given a faithful discretization using this method. So it extends to more than just the PHT. There are other transforms that you might be interested in that don't return dimension exactly. So for example, the Euler characteristic curve transform, and indeed they would fail on if we tried to use this method directly. However, there are some adaptations that we can make. So using the wedges that I just described for the higher dimensional simplex reconstruction, and instead of in degree, we use more of an inclusion-exclusion style argument. We can give a discretization for these other transforms. They take longer and they use more descriptors, but it still gives a faithful discretization. All right.
Thank you so much. Everybody, please unmute yourself and applaud the speaker. Are there any questions for Anna? So actually, while everybody's thinking, let me quickly ask a question. So it was an amazing talk. I'm really interested in these topological transforms. So I have quite a general question. It seems that you got a lot of benefit from this tilting procedure, which suggests that there's a lot of important information, not only in the persistence diagram in a direction, but in the persistence diagrams of nearby directions. So you could imagine packaging that as a kind of derivative of a persistence diagram, where at each point you locate, you sort of keep track of where things move as you adjust as you sort of tilt in different directions. Do you think that, this is a very open-ended question, do you think if you were to package the information of somehow a gradient of a persistence diagram, that you would get something that would require less information to be faithful, or computationally maybe would be advantageous.
I've never thought about it in terms of gradient or derivative, but that's a very interesting perspective. Yes, certainly if you look at the movie, so to speak, of the infinite set, there are certainly redundancies. And you can think of almost like if you swing your direction but don't change the vertex order, in some sense you can almost predict what the persistence diagram will be as you move it. So yes, it would be interesting to think about that more in terms of, as you mentioned, gradient. Interesting question.
It's a very broad question. Thanks for the answer, though. Any other questions from our audience?
I'll be impolite and ask another organizer question. So Anna, my question, so in your talk, you're showing how a finite set of persistence diagrams can determine the simplicial complex, and it's sort of a a finite set of persistence diagrams. Each one is sort of equipped with a label in terms of what direction is that persistence diagram, right? So you mentioned how the first results were working with all directions. So you have you show that if you know the persistence diagram at every angle, this uncountable number of angles, then you can reproduce the simplicial complex. I think it was that Turner reference, right? Is it known if you have the collection of if you have the collection of persistence diagrams, but the persistence diagrams aren't equipped with their direction labels, is it known how much of the shape that determines? So all I give you is a set of the persistence diagrams, say at all directions, but the persistence diagrams aren't labeled with the directions from which they were swept. Is there anything you can do with that, or do people know that's not faithful, or yeah, do you know anything about that?
That's a very interesting question. I would need to think about it more. The first thing that popped into my head is if we have a vertex set and its opposite, would we be able to distinguish between the two if we didn't know the difference between, for example, the downward direction or the upward direction? And I'm not certain.
So just to chime in, so in the original paper, under general position genericity requirements, you can reconstruct it if you throw away the directions. But whether or not any of the reconstruction results in this paper is a very difficult question. Sorry, Anna. Just there's nothing known for this kind of reconstruction in the discrete case.
Thanks. Super interesting.
Hi, just a quick question. Stupid question. When you discretize your step size, does that matter? What step size you choose?
So it's not a consistent step size. Right, when we choose, for example, our tilted directions, there are many different ways of doing that. We're sort of perturbing by epsilon, but we could choose kind of any epsilon within a range. So I guess to answer your question, there's not necessarily a unified step size between the directions we're choosing, and you have a little bit of wiggle room for the step size that you do choose.
Great, thank you.